Problem 12 gives us an interesting projectile motion kinematics problem. It's basically asking which of these two clubs we want to use to hit a golf ball 110 yards or 330 feet. It gives us 9 iron and 8 iron, which those are apparently the angles at which those clubs are from the vertical. I don't know if that's true, but it doesn't really matter. This is what we've been given. And it's asking us which of these two clubs is the correct one to use. So I've just gone ahead and written up some assumptions and done a little quick math to get us started. So first off, we're going to assume there is no air resistance. That's a safe assumption for most projectile motion problems. You do not know how to you do not need to know how to use air resistance in a problem. Second off, these are our knowns. So our initial position is 0. Our final position wants to be 330. Initial position for height is 0, and final position is 0. That's going to help us out in a little bit. X direction acceleration is always 0. Y direction acceleration is always going to be acceleration due to gravity. We're using feet, so it's going to be negative 32.2 feet per second squared. If you don't know that, that's fine. Just say acceleration due to gravity is g, and if they question you on it, just be like, I don't necessarily remember that constant, but I'm going to use g going forward in my equations. Your interviewer shouldn't hold you too accountable for that. If they really care, they'll give you the value. They want to see that you can do the problem and understand the concepts of the problem. This section on the right is just a little bit of quick conversion. So we're given the angle from the vertical, and I need the angle from the horizontal. So 44 degrees, just quickly, we're going to get 46 degrees. 42 degrees pitch, we're going to get 48 degrees from the horizontal. So these are the angles we're actually going to use when we solve this problem. The next thing I did is just convert miles per hour into feet per second. I didn't think you needed to see that math, but here is the equations that I used, gave me an answer, and then I just skipped the math for this one to show you the answer. Okay, so we're in a good spot to go forward. First thing I want to do is basically we're going to be comparing the two situations. So I want to get some standard equations out of the way first. First off, we should probably figure out time. And for most projectile motion problems, you're going to find the time component by utilizing the height. That's not always, but it is a good place to start. If you're looking for time to go into your position equation, probably going to use height because you know the starting and end destination. Okay, so for this, we're going to just use our normal, the most common kinematic equation, y equals y naught plus v naught, in this case y direction, times time, plus 1/2 acceleration in that direction times time squared. So our initial position is 0, but also our final position is 0 for height, plus our initial speed, which is also 0, times time, plus 1/2 g t squared. So when we solve for time, excuse me, I made a mistake. This is not 0. We do have an initial y speed. It's going to be some component of whichever direction we pick, because we have an initial speed of 70 miles per hour or 72 miles per hour at each of these angles. If we solve for t from this situation, we're going to cancel out 1t from the equation, so we're going to get left with v equals negative 1/2 gt, and then t is going to equal negative 2v naught y times the acceleration due to gravity. So for both of our equations, for both of our situations, we can use this equation for t. Okay, and next I want to get some sort of positional equation. So if we use the same equation, but for the x direction, we have x equals x naught plus v naught in the x direction plus t plus 1/2 ax t squared. Okay, so we're going to assume we don't know the end destination because we're looking for which one of these numbers is going to be closer to 330. Our initial position is 0. We have an initial x speed. That's going to be the other component of our initial speed, times time plus 1/2 0 acceleration in the x direction times t squared. So our x final position is equal to v naught x times, this time is the same time that we just solved for, minus 2 v naught y times g. That negative sign is kind of confusing. There is a negative sign explicit in that g variable, so it'll end up canceling out and you'll have a positive position. But for now, that's what we have. So this is our equation that we're going to use in each of these situations. So let's just start with the 9 iron. If we're looking for x, we have v naught x for the 9 iron times negative 2 v naught y 9 iron over g. Let's just go ahead and plug in our equations. So this is v naught x 9 times v naught y 9 times 2 over negative g. Okay, so if we go ahead and get a little triangle going here, if this is for a 9 iron, 46 degrees, this is going to be 102.67. That means this component right here is going to be, let's see, v naught sine theta, and that equals 102.67 times the sine of 46. And then this component right here is v naught cosine theta, which equals 102.67 times cosine of 46. We're not going to go ahead and do that math yet. We're just going to see how these fit into the equation. So we're going to all of a sudden get v naught cosine theta times v naught sine theta times 2 over negative g. So if we simplify, we're going to get negative 2 v naught squared times cosine theta sine theta over g. And then from here, you're just going to essentially plug it into a calculator. This, usually you don't get a calculator for the interviews, and most of the math that you'll do is something you can do by hand. No one's expecting you to solve cosine 46 by hand or multiply it by 102.67. Some of these practice problems come from a textbook situation or a situation where you have a calculator. That being said, sometimes if you get really weird math and you can't do it by hand, you might have a calculator available from the interviewer. That's a situational thing. But that being said, this is a pretty complicated math. If you just plug in all of these values, you're going to get an answer of 327.36 feet or 109.1 yards. We're using g equals negative 32.2 feet per second squared, by the way, in that calculation. So if we use a 9 iron, this is how far we're approximately going to hit it. Now, right off the bat, that's basically 330, but I would advise going ahead and solving the second one just so you can compare and contrast. I'm going to do it a little bit quicker this time, though. So for the 8 iron, we have x equals. We're going to use the exact same setup and formula. We're just going to plug in the opposite numbers. So in this case, negative 2 is going to be 105.6, right, instead of 102.67. Squared times cosine of 48 times sine of 48, all divided by negative 32.2. And this gives you an answer of 344.4 feet or 114.8 yards. And again, we already knew that this was a really great estimate, so the answer is going to be the 9 iron, but just good to do out the problem. Problem 13 is another kinematics problem. And it gives a situation where we hit a ball, it takes an arc and lands some distance away. And it's asking us for how high the ball reaches at its pinnacle. So essentially we can just start with what we're looking for. I think it's a good place to start with most kinematics problems. We're looking for some y height. It's the max height. So if we just write our positional kinematic equation, the most common one we're going to use, it's going to be y equals y naught plus v naught in the y direction times t plus 1/2 acceleration in the y direction times t squared. So what do we know from this situation? We know that y naught equals 0. I have all of our knowns written up here. I do not know my speed in the y direction, so we're going to leave that blank. And I know my t, right? So it gives us a total of 4 seconds, but we know the system's essentially going to be mirrored. So the pinnacle height, assuming no air resistance, which is worth writing down, no air resistance, that there's going to be nothing interfering with the ball. So the highest point the ball will reach is at halfway time, and then it's going to start coming down after that. So I know that time is 2 seconds. I'm going to keep my colors consistent. And then I know 1/2. Acceleration in the y direction is just g. And I'm going to instantly plug in -10 meters per second. And I know 2 is going to be 4 because c of 2 squared. T is going to be 4. Okay. And my final y is the height I'm looking for. So this is essentially the height. If you start at the initial position with the initial speed halfway through it at second 2 with all of these other accelerations. Okay, if you go and solve for this, it's going to be h equals 2 v naught y minus 20. So all we need to do from this spot is find v naught y, and that's going to be found using one of the other equations. So if we look at what we have, we don't really have any information in the x direction, so we're probably going to use another y equation. So the kinematic equation that we're going to use is the v equals v naught plus acceleration times time. This is the second most common equation you're going to use, and if the first one doesn't work, you should use this one, and then the other two are more rare instances. So from this point, if we're looking for v in the y direction, and it goes vy equals v naught y, which is actually what we're going to use, and then we have gt, right? This is essentially what we're looking for. Our final speed we're going to say is at 0.3, and our initial speeds we're going to say at 0.1. So we're analyzing this point right here and this point right here. So once the ball hits the ground, it stops. So our initial speed is going to be, or our final speed is 0. Our initial speed in the y direction is some initial speed plus g times t, but because the full movement has occurred, it's 4 seconds. So our v naught y equals positive 10, because we'll add it to the 0 side, times 4. V naught y equals 40 meters per second. And that's going to get plugged into our equation. So our final height equals 2 times v naught y, which I'm just going to plug in 40 minus 20. And our maximum height is going to be 80 minus 20, or 60 meters. And this is our final answer.